Back in the early 20th century, the world was standing on the edge of massive changes. People were still walking or riding horses, but one guy from a farm in Michigan had a bigger dream. Henry Ford didn't just invent the automobile, he made it affordable for everyone, completely changing how we thought about speed, progress, and freedom. His ideas turned the industry upside down, and his vision proved that innovations can start in a small garage and change the world forever. Henry Ford was born on July 30th, 1863, on a farm near Dearborn, Michigan, to William and Mary Ford. His childhood was spent among fields and workshops, where from an early age he showed a real fascination with mechanics. Although the family hoped Henry would take over the farming business, he himself dreamed of something else, of machines that could move themselves, without horses. One specific event when he was 9 years old had a big impact on him. He saw a steam-powered tractor for the first time, moving without any draft animals. This left an incredible impression on him. That moment became a symbol of the future age of mechanization, which he would later lead. Henry spent hours in the workshop, taking apart clocks and mechanisms. He wasn't just curious about how everything worked. He was looking for ways to make things simpler and more efficient. In 1876, when he was 13 years old, his mother passed away. This became a turning point in the boy's life. The loss changed his perspective, making him think even more seriously about what he wanted to achieve. His father tried to get Henry involved in farming work, but he preferred mechanical experiments. In 1879, when he turned 16, Ford made an important decision. He left the farm and headed to Detroit to work as a mechanic. That was the first step toward his future career. The city opened up a world of opportunities for him. He got an apprenticeship in a machine shop where he gained valuable experience working with engines and mechanisms. After several years of learning and working, he started developing his own ideas. His main goal was to create a machine that ordinary people could actually afford, and that very idea led him to a revolution in automobile manufacturing. In 1888, Henry Ford married Clara Jane Bryant, who became his faithful companion and lifelong support. Clara believed in his talent and dreams, even when others had their doubts. Her support was key in many important moments of his life, including during the creation of his first car and the founding of Ford Motor Company. She not only inspired him, but also helped him maintain balance between his work and family life. Clara also played a crucial role in the creation of the first car. She supported Henry when he spent nights in the workshop, working on his projects. Her patience and understanding were indispensable, as she understood how important it was for him to succeed. Clara often participated in discussing ideas, helping him find the best solutions. So, were you as lucky with your wife as Henry Ford was? Let us know in the comments. The journey of creating Henry Ford's first car was filled with challenges, setbacks, and triumphs. In 1891, he started working as an engineer at the Edison Illuminating Company, where he got the chance to experiment with internal combustion engines. In 1893, he created his first gasoline engine, which became the basis for future developments. In 1896, Ford completed work on his first automobile, which he called the quadricycle. This was a small, four-wheeled vehicle with a gasoline engine. Although the quadricycle was far from perfect, it was an important step in realizing Ford's dream. However, the path to success wasn't easy. In 1901, Ford founded his first automobile company, the Detroit Automobile Company, but it suffered a failure due to high costs and low product quality. Despite this, Ford didn't give up. He continued to refine his ideas and look for new opportunities. In 1903, Henry Ford founded Ford Motor Company, which became a turning point in his career. In 1908, the company released the Model T, a car that changed the world. The Model T was affordable, reliable, and easy to use, which made it popular among ordinary people. Ford also introduced revolutionary production methods, notably the assembly line, which allowed for a significant reduction in the cost of automobiles and made them accessible to the masses. This approach became the foundation of modern mass production. Henry only finished a church school. He never learned to write without mistakes, and even after becoming a company owner, he couldn't draw up a contract without outside help. Later, he would say that for an entrepreneur, it's more important to know how to think than to write correctly. From a young age, Henry Ford had his own revolutionary views on the organization of labor and production. Other industrialists didn't share his aspirations and sometimes openly criticized him. He received no support at either the Edison Illuminating Company or the Detroit Automobile Company. Henry, trying to draw attention to his brainchild, drove around the streets of Detroit in his constructed automobile, only getting ridicule. Locals nicknamed the inventor the crazy man from Bagley Avenue. But this didn't stop his persistence. He dreamed of achieving his goal no matter what, to put car production on an assembly line. In 1914, Henry Ford introduced the highest minimum wage in the States at his plants, $5 a day. He was the first among competitors to allow employees to participate in the company's profits and built an ideal workers' village for them. The Ford concern switched to round-the-clock production. Employees worked in 3 8-hour shifts. The new format allowed for opening several thousand jobs at once. Being a person of Puritan upbringing, Henry advocated for his staff to lead reasonable and sober lives. Employees who drank away their pay and didn't take care of their families were instantly fired. When the United States enters World War I on the side of the Entente powers, Ford betrays his pacifist worldview, and his factories begin working on military orders. This included not only automobiles, but also cylinders for aircraft engines, gas masks, and helmets. Production was modernized to such an extent that Ford Motor Company started producing even submarines and light tanks. In 1925, Ford opened his own airline, Ford Airways, and in parallel with this, bought William Stout's production facility for designing and manufacturing airliners. The first model was a tri-motor aircraft called the Ford 3AT Air Pullman. In 1927, Henry launched serial production of the Ford tri-motor passenger aircraft, which was aptly nicknamed the Tin Goose. This all-metal trimotor model was produced until 1933. In total, 199 of these airliners came off the assembly line. The Ford Trimotor was successfully operated all the way up until 1989. In 1928, for a revolutionary breakthrough in the auto industry and industrial production, Ford was awarded the Elliott Cresson Medal, an honorary award for scientific and technological achievement from the Franklin Institute. Henry remained the de facto head of his own enterprise until the 1930s. Then, due to constant conflicts with partners and union representatives, he was forced to hand over the high office to his only son, Edsel. It's worth noting that saying Henry Ford is the father of the assembly line is actually inaccurate. Assembly line production was used in industry long before him. However, he was the first person in history to successfully put the production of such a complex product as the automobile on the flow line, or on the assembly line. He was also the first to put personnel and production management on a scientific basis. He studied many scientific publications which proved that the division and specialization of labor improve overall efficiency. Later, his approach to organizing production processes would find a scientific name: Fordism. Back in the days when one specialist assembled an engine, he had to spend 9 hours 54 minutes on a single motor. After the process was divided into 84 separate operations for 84 workers, assembly time was reduced significantly, amounting to just 40 minutes. When a car was assembled in one place, 12 hours were spent just on chassis assembly. After Ford introduced mobile platforms and the delivery of parts using hooks and motorized carts, the manufacturing period was halved. Full car assembly previously required 12.5 hours, but after all the innovations, It took just 93 minutes. Ford always added something of his own to the teachings of theorists. For example, he had employees who were paid an hourly wage for doing nothing, and they just sat in the lounge room. This was the assembly line repair crew. As soon as the mechanism stopped due to a malfunction, the salary meter was paused. It stayed paused until the specialists fixed the breakdown. This way, the manager stimulated them simultaneously for both fast and quality repair. Crazy, right? Can I get paid for sitting in the smoking room too? The entrepreneur passed away at 83 years old on April 7, 1947, as a result of a brain hemorrhage. After the death of the famous industrialist, information about his anti-Semitic views and support for the Nazis during World War II increasingly began to surface in the press. Ford Motor Company continues its operations today, although it is facing financial challenges. In the first quarter of 2025, the company earned $500 million in net profit on $40 billion in revenue. This is a significant decrease compared to the same period in 2024, when profit exceeded $1 billion. Despite the difficulties, Ford continues to develop its electric vehicle and hybrid technologies. For example, the Ford Model E division showed sales growth of 210% compared to last year. Ford Motor Company does not yet have its own cryptocurrency, but the company is actively exploring the possibilities of Web3 and the metaverse. In 2022, Ford filed 19 trademark applications related to non-fungible tokens and virtual assets. This includes the creation of virtual cars, trucks, clothing, and an online store for non-fungible tokens. This could be an interesting step in the development of the brand, considering the growing popularity of digital assets. Imagine, every day, in kitchens across America, chicken pieces weighing 3 to 5 ounces are transformed into crispy legends. This ritual starts with 11 secret herbs and spices, hot oil sizzling at 350 degrees, and a piece of chicken plunged into it with a sound that makes your heart beat faster. History, flavor, and technology all come together in one bucket. Somewhere in the distant 1930s, in a forgotten mountainous area of Kentucky, Harland Sanders, an ordinary man with a restless character, stood at his small gas station cooking food for hungry drivers. He didn't have a restaurant, a chef's title, or a lot of money. He only had a slice of ambition, a handful of spices, and a fierce belief in flavor. When customers started coming not for gasoline, but for chicken, Sanders realized he had created something special. His secret? A blend of 11 herbs and spices that he kept in his head, never wrote down, and mixed by hand. The chicken was fried in pressure cookers, which preserved the meat's juiciness while delivering that very crunch everyone was looking for. In 1936, the state of Kentucky awarded him the honorary title of Colonel. Kentucky Colonel. Thus, the image that would become timeless was born. Colonel Sanders in a white suit with a mustache and southern charm. But the real breakthrough came in 1952. Sanders, already over 60, began traveling across America with his skillet, offering restaurants to cook chicken using his recipe in exchange for a percentage of sales. It was a revolution. He launched a franchise when no one even knew the word. By 1960, KFC was already everywhere. The white suit became a symbol, and the chicken, a legend. The company sold millions of portions, and the Colonel himself, although he later sold the business, remained its face and soul until his final days. His figure still stands on every logo, on buckets and packaging. Thus, a simple man from a gas station turned into the Chicken King, and his recipe into one of the most famous gastronomic secrets in the world. Today, production begins far from the city, on specialized farms where broilers are raised, chickens that grow to 4 or 6 pounds in 6 or 8 weeks. Here, everything is precise: temperature, feed, water, lighting, all controlled by automation. The chickens don't roam the fields, but they grow uniformly without stress, which means the meat is soft, tender, without any tough surprises. When the time comes, climate-controlled trucks pick up a batch. Each truck maintains an optimal 40 degrees Fahrenheit to preserve freshness. The chickens are delivered to a processing plant where everything is automated to the level of science fiction. Just imagine, yesterday these chickens were running around a farm in Georgia or Tennessee, warming themselves under lamps and pecking at feed. And today, they are in a giant processing center. Huge trucks with the inscription, "Fresh Poultry Only," drive up to a sterile unloading dock, where the chickens enter a closed cold conveyor. The temperature in the receiving area is 34 degrees. Everything hums, flashes, spins, and workers in white coats, caps, and with a disinfectant spray on their belts are like cowboys with antiseptics. After processing on the primary line, stunning and slaughter, which are carried out automatically, instantly, and painlessly, the carcasses go to the defeathering machine. It's something between a washing machine and a centrifuge. Dozens of rotating rubber fingers gently but effectively remove all feathers in a matter of seconds. Next, internal processing. The chickens pass through a series of blades and nozzles that cut, clean, and wash, all automatically, under the constant control of sensors and cameras. Not a single drop of blood or remnant of entrails goes unnoticed. Infrared sensors detect even microscopic defects. The carcasses are washed, cooled in ice water or a spray shower, and sent on for portioning. Now pay attention, the chicken is never cut by eye. It's scanned, the thickness of bones and muscles is measured, and only then do special automated machines cut it into perfect parts. Thighs, drumsticks, breasts, wings, fillets. Everything, according to a KFC template, approved for every restaurant in the world. For example, a fillet piece should not exceed 3.5 ounces, and a drumstick should be no shorter than 6 inches. Did you know that? Each piece, by weight, volume, shape, is checked a second time. Those that don't quite meet the standards are not thrown away. They are sent to other chains, or for processing into cutlets, sausages, or even dog food. The next zone is quality control, which resembles an airport. Lab technicians in masks take samples, select pieces, weigh them, and enter them into a database. One mistake, and the entire batch goes into quarantine. Because food safety control never sleeps and never forgives. Then, the most important part, cooling and packaging. Here, the meat is placed in airtight trays, vacuum sealed or wrapped in film, and an identification barcode, batch number, processing time, branch name, and even the number of the truck that will transport the meat to the restaurant are added. All of this goes into refrigerated chambers, where it is stored at a stable 34 degrees until shipment. These chambers are like safes, automatic humidity and temperature control, limited access. Even the air is filtered to operating room standards. And so, a truck branded with the familiar red and white KFC logo carries this entire chicken symphony to the kitchens, where fryers, spices, employees, and buckets with happy faces are already waiting for it. The truck opens its back doors, and from it, as if under guard, trays of fresh, chilled chicken meat are unloaded. The temperature, as it should be, is no higher than 36 degrees. The kitchen team immediately receives the batch, checks the barcodes, and records it in the system, because every part, every drumstick is accounted for, like a soldier in battle. And then, the ritual begins. Before breading, each piece is checked by hand, for any damage, excess fat, or cracks. Then the chicken is dipped in cold water, so the breading sticks better. This isn't just a wet dip, it's preparation for a real crusade in the fryer. And here it is, the legendary flour mixture with 11 herbs and spices. Yes, that's the one. Only a few people in the world know the exact composition, and it's guarded better than a nuclear code. The mixture is stored in an airtight container, unloaded into a metal basin, and here the shaking begins. The chicken is tossed in the flour, then it's turned over 13 times by hand. Yes, not 12, not 14, but exactly 13. This is a sacred KFC number, a guarantee of even coating. The employees' hands move rhythmically, automatically, as in a combat dance. Everything must be tight, well coated, but without clumps. Next, the fryer. A fryer isn't just a pot of oil. It's an industrial war machine that maintains a precise temperature, 350 degrees Fahrenheit. It's a hell, so that you can later feel like you're in paradise. The pieces are carefully placed in mesh baskets and submerged. Immediately, SSS, the music of sizzling begins. The oil surrounds each piece from all sides. And now what's important, the chicken doesn't just float in the fat forever. It's fried on a timer, on average for 13 minutes, depending on the part. And what's next? The chicken doesn't go straight to the tray. It's placed on special racks to drain off excess oil. Then, into holding cabinets with heating, where it waits for its moment of glory for no more than 60 minutes. If it's not eaten, it's disposed of. Everything is fresh, without compromise. While the cashier is taking an order, the cook assembles the meal. A few crispy pieces, sauce, fries, a biscuit, and everything into a familiar white and red bucket or box. And then, onto a tray, into hands, into a car, into the heart. And there it is, the crunch, the very same one, legendary. It was born from precision, temperature, secrecy, and ritual. You can't fake it. You can't replicate it at home. Well, unless you try very hard. Because KFC isn't just chicken. It's an industry with the taste of childhood, road trips, first paychecks, and late-night snacks. Every day at factories operating under the KFC brand, over 1.5 million chickens are processed. Yes, that's right, 1,500,000 daily. That's about 17 birds every second while you were listening to this sentence. In a year, that's over 500 million. A chicken battalion that could occupy an entire state. On one portioning line, 150 chickens per minute. The machines don't sleep, the knives don't stop. Each fillet is cut with precision down to 1/10 of an ounce, goes into a vacuum package, is barcoded, and flies to a restaurant that could be 3,000 miles away. Even more interesting, more than 70% of the chickens that KFC sells in the US come from local farms, often family-owned. And every restaurant in the world, and there are almost 28,000 of them in 150 countries, has a standardized taste, verified by a laboratory. Coca-Cola is more than just a carbonated drink. It's a story of ingenuity, marketing genius, and global influence that has changed the way we consume beverages. The origins of Coca-Cola date back to 1886, when pharmacist John Stith Pemberton created a unique recipe that was initially positioned as a medicine, but quickly became America's favorite drink. From a small pharmacy in Atlanta, Georgia, to a global brand known in every corner of the planet, Coca-Cola has followed a path filled with innovation, challenges, and brilliant marketing moves. Its recognizable taste and legendary bottle have become symbols of a culture that unites people of different generations and continents. This story is not just about a drink, but about how an idea can become a global phenomenon, changing the world around it. Coca-Cola is a complex and carefully balanced beverage that combines several main ingredients, each playing an important role in creating its unique taste and texture. The base of the drink is carbonated water, which makes up about 90% of the volume. Carbon dioxide, dissolved under pressure, gives the drink its characteristic fizziness and refreshing effect, which is so valued by consumers all over the world. For sweetness, Coca-Cola uses either high fructose corn syrup or cane sugar, depending on the region of production. In the United States, such syrup is predominantly used due to its availability and cost, while in many other countries, natural sugar from sugarcane is used. These two sweeteners have slightly different taste profiles, which affects the subtle nuances of the drink's flavor, but both provide the same sweetness that millions recognize and love. The color of the drink is created using caramel color, which gives Coca-Cola a deep, dark brown hue. This coloring is produced using a special technology that ensures color stability and does not alter the taste properties. The tartness of the drink is provided by phosphoric acid, which also enhances the refreshing effect and gives the drink its characteristic light tang. Caffeine is another important ingredient that adds a slight bitterness and a stimulating effect to the drink. The most mysterious component is the natural flavors, which contain a secret recipe known only to a select few company employees. This mixture of essential oils, extracts, and spices creates the recognizable aroma and taste of Coca-Cola, which is impossible to replicate exactly. It is known that the composition may include oils of lemon, orange, cinnamon, nutmeg, and other ingredients, but the exact recipe remains a trade secret. In some versions of Coca-Cola, such as Coca-Cola Zero Sugar or Diet Coke, artificial sweeteners like aspartame and acesulfame potassium are used instead of sugar, which allows for reducing the calorie content of the drink without losing its taste qualities. These versions are aimed at consumers who want to reduce their sugar intake but do not want to give up their favorite taste. Thus, the uniqueness of Coca-Cola lies in the combination of simple but carefully selected ingredients, which together create a unique taste and aroma. Each component performs its role, from refreshing carbonation to sweetness, color, acidity, and subtle aromatic notes that make this drink legendary and recognizable all over the world. The production process of Coca-Cola is a true high-tech dance, in which every step is performed with precision and care to create the legendary drink that is known and loved all over the world. Let's imagine we've entered a modern factory where the magic begins. It all starts with water, the main ingredient of the drink. Water comes from special sources and undergoes multi-stage purification. First, it is filtered through sand, carbon, and ultrafiltration systems to remove any impurities, bacteria, and unwanted substances. Then the water is treated with ozone or ultraviolet light for additional sterilization. The result is absolutely pure, crystal clear water that meets strict international quality and safety standards. In parallel, a sugar syrup is prepared. For this, sugar is dissolved in purified water in special tanks. This process takes place at a strictly controlled temperature to ensure the sugar dissolves completely and the syrup becomes homogeneous. The water for the syrup also undergoes filtration to avoid any impurities. The next key stage is mixing the syrup with a concentrate of aromatic substances, which contains the secret Coca-Cola recipe. This mixture is added in special proportions to create the characteristic taste and aroma of the drink. The result of this stage is the so-called blending syrup, the basis of the future Coca-Cola. Then, the blending syrup is mixed with purified water and carbon dioxide in large mixing tanks. Carbon dioxide gives the drink its refreshing fizziness and a light tingling sensation that is so appreciated by consumers. The entire process takes place under strict control of pressure and temperature to ensure the ideal concentration of gas and uniform saturation of the drink. In parallel, packaging is prepared at the factory. Empty glass or plastic bottles, as well as metal cans, undergo thorough cleaning and sterilization. The bottles are washed in special machines where water under high pressure and temperature removes any contaminants. Then they are dried and prepared for filling. After this, the main conveyor process begins. Bottles move along belts at a speed of hundreds per minute. They are automatically filled with the finished carbonated drink through special dispensers that accurately measure the volume of each portion. After filling, the bottles are quickly sealed with caps or lids to preserve freshness and carbonation. Next, the bottles pass through a quality control zone, where special sensors check the fill level, seal, and absence of defects. If any deviations are detected, the bottles are automatically rejected. After this, the filled and sealed bottles move to the labeling stage. Labels with the logo, information about the composition, and expiration date are applied to them. Then the bottles are packed into cardboard boxes or plastic crates, which are convenient for transportation and storage. The packaged products are sent to the finished goods warehouse, from where they are distributed to stores all over the world. The entire production process is accompanied by constant monitoring and quality control. The factory has numerous sensors and computer systems that track temperature, pressure, carbon dioxide concentration, equipment cleanliness, and compliance with safety standards. This ensures that every bottle of Coca-Cola meets high requirements and provides consumers with a consistently pleasant taste. So, the production of Coca-Cola is a complex and coordinated work of a large team and modern equipment, where water, sugar, a secret concentrate and carbon dioxide are transformed into a legendary drink. Bottles and cans, as if on a magical conveyor, go through all stages from cleaning to sealing, to ultimately end up in your hands, with a fresh, sparkling, familiar taste that has been bringing joy to millions of people around the world for over a century. In the first quarter of 2025, the Coca-Cola Company reported a net revenue of approximately $11,113 million, which is 2% less than in the same period last year. This decline was due to currency fluctuations and changes in the structure of franchising operations. At the same time, organic revenue, which takes into account internal growth without the influence of external factors, increased by 6%, indicating a successful pricing policy and a recovery in sales volumes in key regions, such as the Asia-Pacific region. The volume of sales in the form of product units increased by 2%, which is the best indicator since the second quarter of 2024, thanks to growing demand in India, China, and Brazil. Coca-Cola remains one of the strongest global brands with a recognition index of over 90 points, ranking among the top 10 global brands in terms of value and influence. The company is actively developing markets in countries with rapid economic growth, such as India, China, and Brazil, where the demand for soft drinks is growing due to the increase in the middle class and changing consumer habits. Every year, over 150 million cubic meters of plywood are produced worldwide, a volume that could circle the Earth several times in train cars. But few people stop to think that behind this lies a unique technology where wood is literally unrolled into a continuous ribbon and then assembled into a super strong material that can withstand colossal loads. How do ordinary logs, after spa treatments in giant pools and a dance with knives, turn into perfectly smooth sheets, ready to serve in furniture, ships, and even skyscrapers? Watch until the end, and you'll discover one hidden secret of this production that isn't talked about publicly. It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, pine, or other species. After being delivered to the factory, the logs go through the first and very important stage of preparation hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours, and sometimes up to a day. This sort of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible, as cold wood would simply crumble and break. After their bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface. Then the logs are sawn into standard lengths, ready for the main stage of transformation. The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens, something that contradicts our usual understanding of wood processing. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife, installed parallel to the axis of rotation, is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon, just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk, like a scroll of ancient papyrus, turning a 3-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength and stability of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor, while hot air intensely blows on them from all sides. The temperature and speed of the air are strictly controlled to dry the veneer evenly and avoid cracking or warping. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks, ready for gluing. At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, usually based on phenol formaldehyde or urea resins, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table. On top of it, a sheet coated with glue is placed. And here lies the main secret. Each subsequent sheet of veneer is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, the third's lengthwise again, and so on. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split along the grain and evenly distributes the load over the entire area of the sheet. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical, and the outer layers have the same grain direction. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-level structure, between whose plates several dozen future plywood sheets are loaded simultaneously. When the press is loaded, the plates begin to close. With an enormous force, reaching tens of kilograms per square centimeter, the plates compress the veneer layups, turning them into dense, thin blocks. At the same time, the plates are heated to a temperature of 302 degrees Fahrenheit. Under the influence of high pressure and temperature, the glue polymerizes, penetrating into the pores of the wood and permanently bonding the layers into a single, incredibly strong monolith. The pressing process lasts for several minutes, after which a finished plywood board is born. Hot sheets of plywood come out from under the press and are stacked for gradual cooling. This is important to avoid internal stresses in the material. After cooling, the sheets undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth and even. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, cracks, glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a corresponding marking is applied to it. The finished, sorted, and packaged stacks of plywood are sent to the warehouse, to later become part of furniture, houses, ships, and countless other structures, demonstrating to the whole world how human intellect can improve upon nature itself. The global scale of production is also impressive. Annually, over 150 million cubic meters of plywood are produced worldwide. If you were to load all of this quantity into railway cars, the resulting train would circle our planet at the equator several times. The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material for which there are several clearly defined paths. Its future fate depends on the thickness and quality of the wood. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets. Every year, millions of tons of refractory bricks are produced worldwide, a material capable of withstanding temperatures over 1,500 degrees Celsius and protecting structures where metal melts or flames erupt. Just to line one blast furnace requires up to 4,000 tons of this stone that fears no fire. But what gives it such strength? Why would metallurgical giants, cement plants, and glass furnaces grind to a halt without it? And most importantly, what technological secret turns ordinary clay into armor against flames? Watch until the end, and you'll find out what they don't write in textbooks. At the heart of it all lies not ordinary red clay, which is used for building bricks, but its special variety, refractory or kaolin clay. Its uniqueness lies in its chemical composition, where two oxides dominate, aluminum oxide and silicon dioxide. It is their high content and the correct ratio that give the raw material its main property, an extremely high melting point. To give the future product stability and predictability, manufacturers resort to a technological trick. Part of the mined clay is not sent directly into production, but is first fired in kilns at temperatures up to 1,500 degrees Celsius. As a result of this process, the clay loses its plasticity, sinters, and turns into a very strong, stone-like material called chamot. This finished chamot is then crushed and used as the main component, with a certain amount of fresh, plastic clay added to it, which acts as a binder. This approach solves a key problem. It significantly reduces the shrinkage of the products during final drying and firing, preventing deformations and cracking. So, the process begins with the preparation of components. The mined clay and other rocks, as well as the pre-prepared chamot, are sent to the crushing line. Giant crusher jaws break large pieces, and then roller and ball mills relentlessly grind them into a fine powder with a clearly defined grain size. Control of the fractional composition is extremely important because the future density, and consequently, the strength and thermal conductivity of the brick depend on how tightly particles of different sizes can pack together. After crushing, automated dosing systems weigh each component, chamot powder, clay powder, water, and other possible additives, with computer precision according to the recipe for a specific type of refractory. This entire mixture is sent to powerful mixers, where it is intensively mixed until a completely homogeneous mass, known as the batch, is formed. Next, the formless mass must acquire its shape. The most common method is semi-dry pressing. The batch, containing a minimal amount of moisture, is loaded into high-strength metal molds. Then, a press exerts an enormous force, measured in hundreds of tons on it, pressing the mass into a steel die. Thanks to this colossal pressure, the particles get as close as possible, displacing air, and at the output, we get a dense, smooth block with perfect geometry. A green brick. Although it already has its shape, it is still very fragile and not resistant to moisture. The next stage requires not strength, but patience and precision. The green bricks are carefully placed on kiln cars and sent to long tunnel dryers. This is a slow and delicate stage, which can last from 1 to several days. Inside the dryer, a carefully controlled microclimate is maintained. The temperature is gradually increased, and the humidity is reduced. It is important that the moisture leaves the brick as evenly as possible from its entire thickness. Any rush or violation of the regime will lead to the outer layers drying faster than the inner ones, which will create critical internal stresses and simply tear the brick apart with cracks from the inside. When all the physically bound water is removed, the culmination of the entire production cycle begins: firing. The brick enters the fiery tunnel of the kiln, where a true rebirth awaits it. Slowly moving through different zones of the kiln, it is gradually heated to peak temperatures, which for chamot brick are 1,400 degrees Celsius, 100 degrees Celsius, and for high alumina types can exceed 1,750 degrees Celsius. This is not just drying, it is a deep metamorphosis. At such temperatures, complex chemical reactions are triggered, mineral particles soften on the surface and sinter together, forming a strong and dense ceramic structure. In the system of aluminum oxide and silicon dioxide, new crystalline compounds are formed. In particular, needle-like crystals of mullite, which, like reinforcement, permeate the entire structure of the brick, giving it exceptional strength and thermal stability. Having passed the peak of heating, the brick just as slowly passes through the cooling zone. This stage is no less important, as rapid cooling would cause thermal shock and destroy the product that has just gained strength. At the exit of the kiln, a completely new product appears. A hard, ringing, slightly rough to the touch block that is not afraid of fire. Next, only inspection. Each product undergoes a rigorous inspection for compliance with geometric dimensions and the absence of defects, after which it is marked, packaged, and sent to fulfill its main mission, to contain the flame. To realize the true significance of refractory bricks, it is worth looking at the language of numbers. The global market for refractory materials is an industry valued at over 30 billion euros annually, and over 70% of this entire colossal mass of products is consumed by one industry, ferrous metallurgy. Just for the internal protective lining of one large blast furnace, it can take from 2,000 to 4,000 tons of refractories. And one steel teaming ladle, which transports hundreds of tons of liquid metal, eats up several sets of lining per year. A standard Chamotte brick of grade SHA5, which is the most common, weighs about 3.5 kilograms and is capable of withstanding temperatures up to 1,690 degrees Celsius. On an industrial scale, this means that millions of tons of these bricks stand guard annually, containing thermal energy equivalent to the energy of thousands of volcanoes. The field of application of refractory bricks is as wide as the hot processes that form the basis of our civilization. Its main consumer is, without a doubt, metallurgy. Here, it is absolutely indispensable. Refractory bricks are used to line the inside of blast furnaces, where pig iron is born from ore. They are used to line oxygen converters and electric arc furnaces, where pig iron is transformed into steel. Huge steel teaming ladles that transport molten metal are also protected on the inside with a lining of refractories. Moreover, for each zone of the unit, its own special type of brick is selected, capable of withstanding not only temperature, but also the chemical aggression of the melt and slag. The second most important consumer is the cement industry. Long, several hundred meter long rotary kilns, in which cement clinker is fired at a temperature of 1,450 degrees Celsius, are completely lined on the inside with special types of refractory bricks. Without this protection, the steel shell of the kiln would burn through in a matter of minutes. The glass industry also cannot exist without refractories. Huge tank furnaces, where the glass mass is melted at a temperature of about 1,600 degrees Celsius, are lined with special, very resistant types of bricks that can withstand not only the heat, but also the aggressive chemical effects of molten glass for years. Besides these giants, refractory bricks are used in the thermal power industry for lining boilers and furnaces, in the chemical and oil refining industries for lining reactors, and in waste incineration furnaces. And of course, on a much smaller scale, we encounter it in everyday life. It is from Chamotte brick that fireplaces, stoves, and chimneys are built, as it guarantees safety and durability, reliably containing the heat in the heart of our home. Every year, over 100 million small arms are produced worldwide. But only one rifle has truly become a legend: the AK-47, a symbol of simplicity, reliability, and an incredible history. It can be assembled and disassembled in minutes, even in the harshest conditions. And that's precisely why it earned the nickname, the weapon that never fails. In this video, we'll take a first-time look behind the scenes of its production, from a raw steel blank to the final tests at the shooting range. You will see the hidden processes that are usually not shown, and you will understand why the AK-47 has become the most recognizable rifle on the planet. When I entered the factory, I immediately felt that I had stepped into a place with a huge history. The air smelled of metal and oil everywhere, and the sounds of working machines created an atmosphere of important work. In this video, I want to show you how the AK-47 is made, starting from the raw materials and ending with the final assembly. We will see how a rifle, known worldwide for its reliability and simplicity, is born from ordinary materials. Believe me, you won't want to miss this exclusive look at the production process. On the production floor, I noticed how ancient methods are combined with modern technologies. Here, they strive to preserve traditions, but also make the process as efficient as possible. Next to the forging areas stood modern machines controlled by computers. The craftsmen here don't just work with metal. They put their soul into every detail, turning it into a part of a legendary weapon. It seems that every corner of this factory is steeped in history and the pursuit of perfection. The manufacturing of barrels is one of the most important and complex stages. The barrel is the heart of the rifle, and its accuracy is very important. I saw how large metal blanks are turned into hollow tubes with the help of special machines. But the real magic happens later, when spiral grooves are cut inside the barrel. These grooves help the bullet to spin so it flies more accurately. This is a very complex process, requiring enormous precision. Even a small mistake can ruin everything, so attention to detail here is at the highest level. I saw how the masters perform this work with pride and responsibility. Each barrel undergoes numerous checks to ensure it meets all standards. Engineers use special instruments to measure and check the inner surface of the barrel. It really looks like a scientific investigation, because even the slightest defect can affect the accuracy of a shot. They check the barrels with ultrasound, measure the diameter, and look for cracks. All this is done to make every rifle as reliable as possible. At the factory, they use both old methods and new technologies. For example, the stocks for the rifles are still made by hand from wood. The masters choose the best wood, birch or walnut, and process it to be strong and durable. They sand the stocks and cover them with special compounds to make them look beautiful and be strong. This shows that traditions and respect for history are very important here. At the same time, for modern models, polymers are used, which make the rifle lighter and more convenient. Injection molding machines produce plastic stocks with high precision, which helps to reduce weight and improve the weapon's characteristics. This combination of old and new makes the AK-47 truly unique. Quality control is a very important part of the work at the factory. Every detail goes through numerous checks. This is not just a visual inspection, but a real process using ultrasonic tests and magnetic particle inspection. All this is necessary to ensure that there are no defects in the parts that could affect the weapon's performance. Every assembled rifle is checked at a special shooting range to ensure it shoots accurately and reliably. I stood behind protective glass and watched as engineers tested each rifle. First, they checked how all the mechanisms worked, and then they conducted a test firing. This is very important, because even a small problem can cause the weapon to fail at a critical moment. If something goes wrong, the rifle is sent back for rework. Engineers also collect data from the tests to understand what can be improved in the production process. One of the engineers told me that all test results are recorded and analyzed. This allows for continuous improvement of the quality and reliability of the weapon. This process never stops. Every employee at the factory tries to do their part as well as possible. I was amazed that they don't just follow instructions here, but constantly strive to improve every detail, making the AK-47 even better. Applying a protective coating is another important stage of production. This helps to make the weapon durable and protected from external influences. At the factory, they use different coatings: traditional bluing, which makes the metal black and matte, and modern coatings that protect against rust. I watched as workers applied these coatings, and it was clear that they do it with great attention to detail. This is another example of how old and new methods are combined here to create the best weapon. The factory also makes magazines for the rifles. Magazines are an important part of any rifle, and they are given a lot of attention here. They make magazines from durable materials to withstand great loads. Each magazine is checked to ensure that it works reliably and will not fail in combat. I saw engineers inserting magazines into the rifle and checking the feeding of cartridges. This is another important stage that shows how they approach quality here. The most impressive stage is the final testing. In a special shooting range, each rifle is checked by firing it. I stood behind bulletproof glass and watched as engineers fired the rifles, testing them for durability and accuracy. Each rifle goes through a series of tests: single shots, automatic fire, and testing in different conditions. If something goes wrong, the rifle is sent for rework. Engineers collect data from these tests to understand how to improve the weapon. This is a continuous process that helps to make the AK-47 so reliable. When I was leaving the factory, I couldn't stop thinking about the complex history of this weapon. On the one hand, it has become a symbol of struggle and revolutions, and on the other hand, it has been used in wars and destruction. Having seen how much labor and skill is invested in each rifle, I realized that this is not just a weapon, but the result of engineering talent and human labor. Every detail is created with great attention, and this makes the AK-47 something more than just a rifle. It is a symbol of history, traditions, and the pursuit of perfection. The AK-47 is not just a weapon, it is a part of history. It was created to be reliable and easy to use. It can be disassembled and assembled in minutes, even in difficult conditions. This makes it popular among military personnel around the world. The simplicity of its design and high reliability are what make the AK-47 so special. Having seen how it is produced, I understood that every detail matters. Every screw, every barrel, and every stock is created with enormous attention to detail. Every year, the world recycles millions of tons of wood waste, and a large part of this trash gets a second life in the form of what we see every day at home, at work, or in stores. Particle board. Imagine this: mountains of wood chips, sawdust, and old furniture being transformed into smooth panels, capable of holding weight, keeping their shape, and becoming the foundation of modern interiors. But how is a monolithic material, with a perfect surface created from a chaotic pile of scraps? In this video, we'll show you every step, from metal separators that pull nails from the waste, to giant presses with temperatures over 400 degrees. And if you watch until the end, you'll discover a secret that will change your perception of furniture. It all begins at a huge raw material yard, where the foundation for the future particle board arrives in a continuous stream. This is a place where the idea of rational resource use is brought to life on an impressive scale. Contrary to popular belief, high-quality commercial timber is almost never used for particle board production. Instead, the production philosophy is to give a second life to wood waste, turning what was previously considered a byproduct into a valuable material. Piles of raw material, reaching tens of feet high, are brought here. The base is technological chips, obtained from low-quality wood that is not suitable for lumber production. A huge share consists of waste from sawmills, slab wood, which is the side parts of a log with a rounded surface, board offcuts, and thin strips that remain after log cutting. Woodworking waste, such as shavings and sawdust, generated at furniture and carpentry factories during planing and milling, is also actively used. A separate and important direction is secondary wood. Old wooden pallets, crates, packaging, and even used furniture, after a thorough cleaning process, get a chance for a new life as part of a particle board. Every batch of incoming raw material undergoes strict incoming inspection, as purity is the key to quality. The first stage of cleaning is the removal of metal inclusions. Powerful electromagnetic separators, capable of pulling a steel bolt from a distance of several inches, sift through the stream of raw material. removing nails, staples, and any other metal fragments that could catastrophically damage the expensive shredding equipment. Next, the raw material passes through screening systems to remove mineral impurities, sand, stones, and other debris that act as an abrasive and quickly dull the cutting tools. If whole logs are used in production, for example, 20 feet long, they must pass through a debarking machine. In a huge rotating drum, or with the help of special cutters, the bark is removed from them. This step is critically important, as bark has a different structure, contains a lot of dirt, and significantly worsens the quality of wood chip bonding, as well as negatively affecting the appearance and strength of the final product. The prepared and cleaned wood begins its journey on a conveyor belt hundreds of feet long, which relentlessly carries it to the first stage of mechanical transformation. It disappears into the steel maw of a giant chipper, an industrial monster the size of a small room, capable of swallowing pieces of wood several feet thick. Inside this machine, with a deafening roar that makes the workshop floor tremble, a massive disc equipped with razor-sharp knives rotates. Rotating at a speed of thousands of revolutions per minute, these knives cut into the wood with incredible ease, turning whole pieces into a stream of uniform chips a few inches in size. But this material, despite its uniformity, is only a semi-finished product. The resulting chips are too large, coarse, and non-uniform in shape to create a quality particle board. Their cubic structure would not allow for the creation of a dense and monolithic structure. Therefore, the next step is a finer and more delicate secondary grinding, which takes place in specialized flakers or mills. It is here, in the hum of high-precision equipment, that the very particle that gave the final product its name is born. At this stage, the geometry of the chip becomes crucial, as it is designed with engineering precision. For the outer, face layers of the particle board, which will be responsible for its appearance and smoothness, very fine, thin, and flat flakes are needed. They are produced in knife ring flakers, which literally shave thin flakes from the chips, resembling flakes only a few hundredths of an inch thick. These flakes, having a large surface area, perfectly bond with the resin and form a flawlessly smooth surface, ready for further processing. In contrast, for the inner central layer of the board, which is its structural backbone, larger and thicker flakes are used. They create a strong internal frame that gives the particle board its final rigidity, bending strength, and the ability to securely hold fasteners, such as screws and bolts. The resulting chip mass has varying moisture content, which is unacceptable for quality bonding. Therefore, all the chips are sent to one of the most important stages, drying. Usually, huge drum dryers are used for this. The chips are continuously fed into a rotating drum, where they are blown with hot air or flue gases. The process is strictly controlled by automation. The final moisture content of the chips must be in a very narrow range, from 2 to 6%. If the chips are over-dried, they will not be properly saturated with glue. If they remain too moist, during hot pressing, the excess water vapor can rupture the board from the inside, forming defects. The dried chips are not uniform in size. To create the correct 3-layer structure of the board, they must be sorted. The chip mass passes through a system of mechanical screens or air separators. Heavier and larger chips, intended for the inner layer, settle first. The lighter and finer fraction for the outer layers flies further. This process allows for obtaining 2 or more streams of chips of different geometries, which will be used to form the sandwich of the future board. Now it's time for the key component that will turn the loose mass of chips into a monolithic board, the binder. Most often, these are synthetic resins, mainly urea formaldehyde or melamine urea formaldehyde. The sorted chips enter special continuous mixers. Inside them, the resin is sprayed through nozzles, creating a glue mist that evenly envelops each particle of wood. The dosage of the resin is critically important and is usually from 6% to 10% of the mass of dry chips. Along with the resin, other components may be added. The resinated chips, now sticky and ready for bonding, are finally ready to become a board. They are transported to a massive forming machine, where a continuous chip mat is born from the scattered particles. It is here that the engineering magic of creating a 3-layer structure takes place. The forming machine is a complex system that sequentially and with high precision sprinkles chips onto a moving conveyor belt. First, it creates a perfectly even bottom layer, using the smallest fraction of chips. Immediately after this, a much thicker middle layer, consisting of large and strong chips, is laid on this base. Finally, the entire mat is covered with another layer of the fine fraction, creating a mirror image of the bottom layer. This carefully designed structure, resembling a sandwich, provides the unique properties of the future board. Its smooth and dense outer layers are ideal for further sanding and laminating, while the strong inner layer gives the board the necessary rigidity and the ability to securely hold fasteners. The formed but still loose mat passes through a pre-press, where it is significantly compacted. This pre-pressing removes excess air from it and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut into fragments of a given length mat is fed into a hot press. This can be either a giant multi-opening press of periodic action, which simultaneously compresses a whole stack of boards, or a modern continuous press of the belt type. Inside the press, the chip mass is simultaneously affected by 2 powerful factors. Huge pressure, reaching tens of kilograms per square centimeter, compresses the chips, leaving no voids between the particles. At the same time, the press platens, heated to a temperature of 400 degrees Fahrenheit, transfer their heat to the mat. This high temperature activates the resin, launching an irreversible polymerization process. The liquid glue instantly turns into an extremely hard and strong polymer, which permanently glues millions of wood particles together. The time spent in the press depends on the thickness of the board and usually lasts only a few minutes. During this short period, the loose mat turns into a hot, hard, and absolutely monolithic particle board. The hot boards after the press cannot be stacked immediately. They need to be cooled gradually to relieve internal thermal stresses and avoid further deformation or warping. For this, they are placed in special star or fan coolers, where they are blown with air for several hours until they are completely cooled and their structure is stabilized. The next step is calibration and sanding, which gives the board a marketable appearance. The boards pass through sanding machines with several heads, where wide abrasive belts remove a thin surface layer, bringing the board to a precise specified thickness and creating a perfectly smooth surface. At the final stage, the large technological boards are cut into standard commercial formats, and their edges are trimmed. The finished product undergoes strict quality control, where its density, bending strength, moisture content, surface quality, and dimensional accuracy are checked. Only quality boards are marked and sent to the warehouse. From there, their path lies to furniture factories, where they will be transformed into familiar household items, silently demonstrating the amazing journey from unnecessary chips to a functional and indispensable foundation of our comfort.